Hello and welcome. In this video, we're going to take a look at augmented matrices and the kinds of solutions that might arise once you get the matrix into a reduced row echelon form. Now, we've already seen this with systems of equations that we can possibly get infinitely many solutions, or it's possible to get no solution. Let's put that into a theorem here and make this more about augmented matrices now. So a system of linear equations will have one of the following types of solutions: a single unique solution, infinitely many solutions, or no solution. Now, when we say infinitely many solutions, we actually give that a term. So we refer to that as an underdetermined system. And in the case of no solution, we call that an overdetermined system. And furthermore, if we happen to have fewer equations than the number of variables in our system, then we cannot get a unique solution. We can either have infinitely many solutions or we can have no solution. So thinking about that, multiple variables but fewer equations. And an equation is kind of like a constraint. So if we have very few constraints, then the system is probably underdetermined and we can have many solutions. But if one constraint disagrees with another and it's impossible for any set of values to agree with both constraints, then it is still possible to have no solution. Okay, so to put this back to augmented matrices, let's take a look at an example or two. Let's do the row reduction on it and get it into reduced row echelon form, and then see if you can tell from that augmented matrix whether or not the system is overdetermined or underdetermined. Okay, here I've got three equations and I've got three variables. And maybe you would like to just try this on your own here. You could pause the video and see if you can row reduce this down to reduced row echelon form. Now, I will go through this one step at a time, and you can also pause at each step to see if you can check your answer that way. So first of all, let's try to make sure that we get that first pivot position as the 3. We want to make that a 1. So I'm going to divide row 1 by 3. Next, I'm going to clear out the remaining entries from that same column. Row 2 becomes row 2 minus row 1. Row 3 is going to be replaced with row 3 minus 2 row 1. Now, right away, something peculiar happens at this point, and you can see that row 3 is now entirely just going to be zeros. There's only one more thing left to finish this off to get this into reduced row echelon form, and that's to take row 2 and divide it by 2. Okay, you can see my two pivot positions both have leading 1s. The columns have zeros, and I have a row of zeros at the bottom. So I can't continue to use Gauss-Jordan elimination beyond this, because in the third column, third row, I can't make a 0 into a 1, so I must be done. Now, what kind of a solution is this? If we were to maybe write this out as equations, let's suppose our variables are x, y, and z. And then, of course, the last column in any augmented matrix is just going to represent constants. Then, translating this into equations, I would have x plus 0y plus 2z equals 5. And my second equation, y minus z equals 4. And I don't have an equation of the form z equals anything. Now, this is what we would say is an underdetermined system. We don't have a determined value for x, y, and z. We have z being a free variable. Z could be anything, and we could still plug those values into this problem and find out what x and y would have to be just by substitution. So, this is underdetermined. It means that we have infinitely many solutions, and we should come up with a way to represent any solution that we want. Z is a free variable. It can be anything that we like. So let's assign it a value. We'll call it a parameter. Let's call that parameter t. And let's assign z equal to t and see if we can express a solution in terms of that parameter. Now, first of all, each of these equations, they form a system, and that system can be translated into x equals 5 minus 2z, y equals 4 plus z, and z is a free variable. And then if we assign z to equal t, then we can write the system out in terms of t. X, y, and z. And if z is equal to t, x is equal to 5 minus 2t, and y would equal 4 plus t. And as an ordered triple, x, y, and z could just equal 5 minus 2t, 4 plus t, t. And any choice of t will suffice for this problem. Now, I will note that depending on the application, wherever these equations came from that we were asked to solve, it may be that certain values of t put the values of x, y, and z outside of their domain. So be careful with the problem. If there is some sort of requirement that we only have so much available for x, y, and z, then maybe you have to restrict t to being a certain subset of the real numbers so that x, y, and z all fall within the specified domains. Now that we've seen an underdetermined system, let's see what it would look like if we ended up with an overdetermined system, something that has no solution. In this example, once again, I've got 3 equations and 3 unknowns. And we could let those be A, B, and C this time if we like. Instead of x, y, and z, or x1, x2, x3, it really depends on the application as to what you might want to name each of these variables. Now, once again, maybe you would like to just take a moment and see if you can get this into reduced row echelon on your own, and then I will just be going through each step one by one. Okay, the first pivot position is already a 1, but we need to clear out row 2. So row 2 is going to get replaced with row 2 minus 2 row 1. All right, now row 2, we're going to find our next pivot position in the second position, and we'll take row 2 and we'll have to divide it by -2. Now the next step is going to be clearing out the rest of column 2. We'll have to do a row operation with row 1, replacing it with row 1 minus 2 row 2. And row 3 will have to be replaced with row 3 minus 1 row 2. Now doing that, it appears that we are in reduced row echelon form. And you can actually see in the third row, our leading one is actually in the column of constants over here. And now we could continue to use Gauss-Jordan elimination here to clear out the values above that 1, but it's not necessarily worth it, because if you take a look at what the implication of this third equation is that 0a plus 0b plus 0c equals 1. So row 3 is actually the equation 0 equals 1. And that is false. And no matter what we try to do with remaining pivots, if we wanted to clear out the rest of the constants column, well, we're just going to end up with equivalent matrices that still involve this equation, 0 equals 1. So this is false, and that means that no matter what the values are for A, B, and C, there's no solution, and this would be an overdetermined system. In other words, there's no solution. And of course, there'd be no way to represent this as an ordered triple. And you can kind of think about this, may be applicable to daily life, especially right now with the pandemic and all the deadlines and everything you have to keep track of at home. It kind of feels like our schedules are a little bit overdetermined and there's no solution to it. Hopefully that kind of makes sense. That's how I like to think about overdetermined. There's far too many restrictions. I can't possibly obey all of these restrictions. And you can see from this example, trying to put all of these constraints on the variables ends up with an equation 0 equals 1, which is impossible. So hopefully that gives you a little bit of an idea as you're going through the row reduction process, the Gauss-Jordan elimination. You should be able to kind of tell probably towards the tail end, maybe a couple steps before you finish, as to whether or not this system is going to be overdetermined or underdetermined. And if you see it's going to be overdetermined, then you can stop. You can already see that there's an equation that's impossible to solve. But if it's underdetermined, then continue to use your process of elimination and then try to give yourself some way to express the solution in terms of a parameter. And it is possible that you can have more than one free variable. it's possible, especially when we have problems involving more than 3 variables, that we have several free variables, in which case you'll have several parameters. And when we run out of letters, we can start calling the parameters T1, T2, T3, that kind of thing. But that could be something that we may see more as an application for a computer. Maybe we'll see one example in class that has 2 free variables, but we tend not to have to use row reduction by hand for large matrices. That's really the job of a computer. Well, anyway, thanks for watching, and I'll see you again in the next video.